Apples. What do we do with apples? I've been using this story for many years. Okay? Here come the apples, folks. You go in here. Now, apple pies are great, but what I want to make is apple cider. Okay? So I'm coming through a function process here, and I'm creating an output, right? Apples come in and creates cider. Okay. Your input, your output, alphabetical order, A and C, apples and cider, okay? Now, before I continue that story, let's take a problem that's in the book. Let's say we took a problem that's in your homework, happens to be 2x minus 6. Let's say we have a process called f of x equals 2x minus 6, and another function called g of x is 1/2 x plus 6. This is number 49 on page 254 in your book. Okay. Now what they asked people to do here was the following. Take one function and put it into the other like we studied in the last session. So let's form f of g of x and see what happens. So if I take this original function f, it says take the input, multiply it by 2, and then subtract 6 from that. So now what I'm going to do is I'm going to take 2, I'm going to take my input now is my entire g function, so I have to insert there 1/2 of x plus 6, and then on the tail end of that, make sure I subtract 6. F of g of x. I now clean up the math here. So I end up 2 times 1/2 is 1, so I get x plus 6 minus 6 equals x. Equals x. Back to my story. If I take my apples and I run through a process and create apple cider, and now I'm going to build a new machine over here where I'm now going to take this cider and feed it in to a machine that does the reverse process. So I pour in the cider and I get back apples. Nobody's built that machine yet, right? But nevertheless, it's the reverse process, isn't it? Okay, so what happens if you would take, and let's call this machine here, instead of f, let me call it g of x. G of x creates the cider. And then I take that cider and I pour it into a machine called f of x. And so what I'm getting out the door over here is f of g of x, where one machine is the reverse of the other, and you get back what? What you originally started with. So everybody can remember this little story. If you take a function and create an output, and then you take and run it through what's called the inverse process, you'll get back what you started with. Back to the algebra. Here we had two functions given to us, f of x, linear function, g of x, linear function. What would you expect these two graphs to look like compared to each other? Remembering the story that we just talked about here, back here. Okay, so let's draw this. Let's draw this and see what happens. So let's draw these two functions on the same graph. So if we draw the first one, 2x minus 6, we have an intercept, y-intercept down at minus 6. with a slope of 2, which means it's going to have an x-intercept at 3, right? And so here it sits, nice steep line here. Feel good? Okay, and then let's draw the other one. This is a 1/2 x graph that is shifted 6 to the left. You see it that way? Differently than, I mean, what you probably do if you were back in intermediate algebra, you'd be thinking of it as 1/2 x plus 3. But if you can see it in terms of its transforms, it's like y equals x, it's half as tall, and then shifted 6 to the left. So you shift it 6 to the left. And make it a slope of 1/2, which means it would have a y-intercept at 3. And an x-intercept over here at -6, 0. And so it's going to look like this, and I'm going to draw it solid. So do you notice what happens here? Look at the two graphs. -6, 0 becomes 0, -6. 0, 3 becomes 3, 0. And out here somewhere, the x and the y readings are the same. X and y readings happen to be the same, which would be where? If you set f of x equal to g of x out there, we have our 2x minus 6 equals 1/2 of x plus 3. Well, if I don't put the parentheses. And then I solve this by multiplying both sides by 2. Since it's a fractional equation, the best way to deal with fractional equations is first of all multiply both sides by the common denominator 2. So I get 4x minus 12 equals x plus 6, multiplying both sides by 2, and then combine these, get 5x equals 18, x equals 18/5, which is 3 and 3/5. 3 and 3/5. Is that right? It doesn't look right, does it? Look at the graphics. The graphics don't look right. So is there a mistake in my algebra? Somebody said something. Excuse me?
3x equals 18.
Minus the
x is minus.
This would be a...
You look at the x and you take it through.
You added the x.
You're going to subtract it from 4x.
Ah, thank you. Okay. Do you see how, and I've suggested previously that you always draw a sketch if you can. And do you see how I blindly went along doing algebra, unintentionally, screwed it up, but I'm able to look at this and I look at my picture and I go, man, that doesn't look, that's 3 and that's just a little bit here. That doesn't look right. Even on my rough sketch here, that doesn't look right. So I go back and investigate and I see, oh, that's not a 5x here, that's actually a 3x, which then gives us a nice value of 6 for the x reading, where the y values are then identical. So this point happens to be 6, 6 is where those two intersect. And I think you can clearly see that if we would draw in here the line y equals x, you can see clearly that one graph is the roll of the other across the line y equals x. Okay. So if we had this a function right down here called f of x, originally defined as our function, passes a vertical line test, doesn't it? A nice linear function. If we create its inverse, we get this thing, right? So here's what we can do. Since the combination of the two f of g of x, one function, its output fed into the other one gave us back x. We could do that in reverse, couldn't we? And we should still get x back if we do it. All right? So if you get that back when you compose one with the other, then that means one function is the inverse of the other. The result we got out of here is an inverse function. This thing is a function. And so if your original function had a defined symbolism, like f of x, here's what they invented if the new thing is a function. If the new thing is a function, we call it f with a little -1 exponent up there, or superscript. We can use that sort of notation. That doesn't mean 1 over f of x. That doesn't mean the reciprocal. This means specifically that you started with some function and you created its inverse by interchanging x and y, and you got something new that was a function also. I think we should practice a little bit. So let's go to that section in the book where we're talking about functions and their inverses, and let's pick a problem out of the book. A quick observation here. Notice that a linear function that we started with has an inverse that is a linear function. What would you expect the inverse to be of a quadratic? Be careful. What's the reversing of a process? What's an undoing of a process? Remember, kind of like the apple juice story. What's the undoing of a process? That's called an inverse. And what happens if you start with a square? How do you undo squaring? Square root. Okay, so if you have a function that started out as a square, like a quadratic, its inverse will be a square root type of function.
But it won't be a function.
Right. If you lay a parabola on its side, like this, right? If you lay it on its side, it doesn't pass a vertical line test, does it? So what you have to do is you have to restrict the domain or the range of the original expression to make the result actually be a function after you do the inverse. Okay, now that's a lot of talking. I think we actually need to do some doing. So let's go ahead and grab something out of the book.